Oh,
how about now? Oh, it's going! Okay, I'll move it closer. Okay, so what we have covered to this point is that we have said this is the Advanced Process Control Lecture Series. The book that we are basing all this on, or a lot of it, the Nonlinear Systems part, is this book by Khalil called Nonlinear Systems. He is a professor at Michigan State. Woohoo! That's not far away. Then there's lecture notes from Professor Christofides is what these are being based on, Professor Christofides at UCLA. Then, okay, cool. So here we go. So, let's go to talking about where people have left off if they are undergraduates. So, if you are an undergraduate, this is probably about the last sort of thing you remember seeing in control. Some block diagram, the controller transfer function, the process transfer function, the output, the set point, and then here's the input. That look familiar?
Yeah.
Cool. So then this is a feedback control loop. Here, the way that we model our output is that it's GPU is what this block diagram is reflecting. So that essentially our output, the derivative of the output is related to the inputs. If we go back out of the Laplace domain, here's the controller transfer function. So the control action is the controller transfer function times the error. Then, and so the limitations of this, one thing, is that transfer functions only hold for linear systems. So essentially, linear systems only. If you're wondering why that is, the way to think about that is what transfer functions. So transfer functions come from taking the Laplace transform. We take the Laplace transform. Laplace transform is a method for solving systems of linear differential equations. And as you know from differential equations class quite long ago, when there were certain sets of equations that can be solved analytically, like separable ones where it's like x dot equals x squared. Oh, you bring it to the other side, you integrate, you do this thing. So turns out linear systems you can solve with the Laplace transform. And then people said, oh, well, if I'm going to work with linear systems, it turns out that there's all kinds of properties because it's linear where I can do things like what's written here. And so essentially this is just mathematics and using properties of how the mathematics of those systems are in order to do control theory. But so now, since this is called advanced process control, we're moving away from linear systems and we're saying, you know, nothing in chemical engineering is mostly a linear system, almost ever. So, all of this, despite that it's really good, is not the direction that we're trying to head in advancing the field. So, let's just set the stage of this. Good versus bad. So, is that bad? No. The linear stuff is not bad. As you know from learning it in undergraduate control, industry uses this. Everybody's using this. It's great. There are many great things about it. It's practical. It's easy. Very computationally straightforward. So many great things about it. It works. People have used it for a long time. So bad things are though that there's certain advances you might want to try to make where linear systems is not enough. If you're operating near a steady state, that can be fine. You can linearize. Mostly this can work. There's a lot of things like accounting for actuator saturation or accounting for the nonlinearities that are really in there if you want to try to advance your ability to make money, etc. Then you might have to start looking at a nonlinear systems perspective to do those things. But it's not that PID is bad. It's not that transfer functions and linear control theory are bad. It's just they're just different. And it's what we do in control is we learn a set of tools. Just like when people will do anything, like when you learn a coding language, you maybe learn multiple. It's not that Python is bad and C++ is good. That's not the way. It's just they're useful in different circumstances. So then now we're going to define some notation. So this is notation that we always are going to use in nonlinear systems. So this is for a nonlinear system. This is what I'm going to use to represent systems of nonlinear differential equations that have inputs so then we can write one for dx2 over dt equals x2 dot equals f2 of t x1 dot 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 xn u1 dot 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 up. Let me close this door to reduce background noise. Okay, then dxn over dt equals xn dot equals fn of t x1 dot 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 xn u1 dot 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 up. Is this catching all of this? Maybe I'll bring it down slightly. Hopefully it's not missing anything. Okay. So this is just notation, but just to make sure everyone's clear on what this is, what we're going to use. So we're going to call x1 dot 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 xn as the state variables. Just to clarify this point, this is similar to the concept of outputs in the undergrad control class, but it's not exactly the same. Because when you have a system of nonlinear differential equations, so outputs is when you measure it, you don't necessarily measure every state. Like if some of these are concentration, some are temperature and stuff, maybe I only measure the temperature, and then, but that doesn't mean that the concentration is not evolving over time. So the concentration remains a state, but the temperature is both a state and an output. Does that sound good?
Mm-hmm.
Okay, cool. Then, so then U1 to UP are the control or input variables. That is very similar in concept to what you did in control class, except that another thing to note here is these are multi-input systems and could be multiple output, which most likely in control class you covered single input, single output. So then notation with regard to vectors. So x is equal to x1 dot 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 xn is contained in R to the n. So that's notation that we're going to use. So whenever I write x, what I really mean is an n-dimensional vector. And then this signifies to me that x is a n-dimensional vector with real entries. Then we have, I'm going to have to start erasing this. We then have that u is equal to u1 dot 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 up is contained in RP. So because we have p entries here, this is in the RP space. And then we're also going to denote f of t x u is a vector function. So it's a function of the time t, the whole vector x, so it can be a function of any of the components of x, and then also of u, so it can be a function of any components of u. And when we write this, what we mean is a vector function, so that there's vectors and each one is a function of the different variables t, the vector x components, and the vector u components. It doesn't have to be a function of every single one of them, Like this, for example, could just be like x1 squared plus x2 squared. We can still use this notation in general because you could imagine that as being like 0 times t plus x1 squared plus x2 squared plus 0 u1 plus 0 u2 or something. So, okay. Any questions on that notation?
The number of states should be greater than the number of inputs, n greater than p, or n should be, what is the relationship between these two?
That's a good question. I don't know from like a controllability and theoretical viewpoint on that, like what happens if your number of inputs is greater than your number of states. But I know that in theory you could write a differential equation where you say like, say this was that temperature dot is equal to the temperature plus something something related to the heat plus something related to the like enthalpy with the inlet flow rate or something, and say that both Q and flow rate here are changing. So in this case, it seems like I have one state and two inputs, but then I guess it could be argued like, well, do you want to model the other states? I don't know if there's...
But I think if P would be greater than N, I think we would have more degree of freedom. So I think it would be the best if you have more inputs than states. But actually have the opposite, right? More states than inputs.
Yeah, I actually haven't really thought about that before. I know there's some theory on something called controllability, but I don't really know what it is. It's like a theory on whether or not you're able to, like under what circumstances on the differential equations can you drive the system to certain conditions. I haven't really looked into that, so I don't know if that speaks to your question.
Okay.
I unfortunately do not know the answer to this. You will have to email me after, Enrique, and have me look, because I should learn these things so I can answer your questions.
Thank you.
Great question! So then with this, we're going to use this notation, so x dot equals f of t xu. This is what you're going to see everywhere in these lectures. And that's going to represent the original system of differential equations when I wrote it on the board over here, and it was like x1 dot equals this, x2 dot equals this. And then, so that's so this is one type of class of nonlinear systems. We can also write, this one is called Input-affine. So an Input-affine class of nonlinear systems is x dot equals f of x plus g of x u. So the input appears linearly, meaning that the input isn't like squared, it's not sine of the input, etc. This is actually very common to see systems of this type in chemical engineering, because a lot of times we'll have something like such and such times the flow rate, and the flow rate's variable, or such and such times the heat input, and the heat input's variable. So oftentimes this is good, but it's not it is more general to use this, and there are a lot of systems in chemical engineering that would also fall in this class. So this one is included in this one, but this is more restrictive.
Input-affine does not account for disturbances.
Oh, that's a good question. I think you could have an input-affine system with disturbances, and you could make this one with disturbances too. This is more referring to the fact that the input is appearing linearly instead of non-linearly.
Okay.
You asked such good questions.
Thank you for the answer, Helen.
Yeah, thank you for asking. So yeah, those are the initial things. One thing that's really difficult about nonlinear systems is that they're just so general, because like if I just want to say, okay, right-hand side of this differential equation is almost any nonlinear function I can imagine in my head, then we can see that that gives a lot of trouble to us in trying to understand their solutions. And so that's kind of, I think, why nonlinear systems theory gets so interesting and control design for it gets so interesting. Because we're dealing with a very complex problem in the sense that if you try to imagine what just happened, so when you're using linear systems, then you say like, okay, I have systems of differential equations with a very specific form and very specific properties. And then you go to nonlinear systems and you say like, oh, like now I'm like open up to so much more. Like I don't just say like, oh, okay, it was like a linear system plus x squared. It wasn't just that. It was like anything else that I thought of, or not anything, but you know, like it became very, very broad very quickly. And then so this is the way science kind of is described, is by these nonlinear systems, and that we don't want to put lots of restrictions. But it is interesting then as you try to like imagine, okay, that's like such a leap going from like so heavily restricted to so heavily unrestricted, that then it does pose a lot of challenges and a lot of abstraction. So that's that. Okay. To demonstrate how this notation would get applied, we're going to look at a CSTR. So this is showing that chemical engineering processes, even the like very simple ones that we use as basically model systems that are not exactly real world systems, if you go to even one of those, the very simple things we do, you'll already see that, okay, everything is a nonlinear system. Or not everything, but a lot of things are very quickly nonlinear. So we have this A to B reaction in this tank, so not even a complex reaction, just one single one, two reacting things, one reactant, one product. Here's the inlet concentrations, the inlet temperature, the flow rate. The flow rate we even assume is constant, volumetric flow rate, I mean. Then we have these concentrations of the two species out and the temperature coming out. And then so then you can write the equations, and we can see fairly quickly that we are getting these nonlinearities here. And I'll write up what are the states and inputs in just a second. So this is just with a ton of simplifications. But already we have this nonlinear system where our states, what would the states be here?
Temperature and concentration.
Exactly. Great job. CA and T. And then, okay, cool. And then we can select some of these to be inputs. So input selection is part of control design, where you choose what's available for you to manipulate and if you're going to manipulate it or you're not.
Mm-hmm.
And so then...
Is first order reaction?
Oh, yeah, you're right.
Mm-hmm.
Thank you.
Mm-hmm.
Good point. Then, okay, cool. So it turns out that a lot of times in chemical engineering, as you can see from these models, that we don't usually have an explicit dependence of time on the right-hand side. I do not think I have ever seen in a model of chemical engineering, not that there couldn't one exist, but I have never seen a case where you have like plus t or plus t squared or anything where there's an explicit t dependence on the right-hand side. So it's reasonable that we're going to start by talking about a type of system called autonomous. So let me make a few simplifications and show what's going on. So first, we can, if we have t, x, and u, to develop, as you know from the way nonlinear systems, or linear systems in undergrad class goes, you start with dynamics, and then once you understand how the systems can behave, then you move on to saying, and here's the way that I'm going to develop inputs for that system. So we're going to take the same approach here to understand how qualitatively, or even quantitatively as well, do systems of nonlinear differential equations behave, to the best that we can do that quantitatively, considering that they behave in many different ways. But then this will then mean that we're going to kind of not consider explicit inputs yet. Not consider explicitly yet. I think I spelled that wrong. But then that doesn't necessarily mean we're considering systems with no input at this time. It means that either one, there is no input, so it's like the way that you handle dynamics when you first do it in undergrad class, where you just say, okay, here's the dynamics of the system. If I change such and such a thing, like, I go to a different initial condition, what does the state do? So that would be having no input. So that's one option to get x dot equals f of tx. Another option is that in advanced control, we develop a lot of controllers. Am I going too fast or too slow?
Good.
Is it okay? A lot of what happens in control is we develop controllers that are explicitly functions of the state. So it'll be things like u equals like x squared, just like how when you had u with PID, like it was kc times the error, so it was y minus y set point, or the other way around, because when you are off the set point, minus y, you want to increase if you're below. So when you have this here, the input is a function of the output. So we can also for nonlinear systems, we can make our inputs be functions of our states. And so if you do that, then that means that you don't need to write your right-hand side as a function of u anymore. You can write it like, say I have this case. So say I have x dot equals x squared plus u, and then that u is equal to x squared. So now x dot is equal to 2x squared, with that input being the way I apply it. So then now you can still, in this case, if you write your inputs as functions of the state, so inputs where u is equal to some, like p of tx, so it could be a function of time and of the state, then you get it so that still x dot equals f of tx. So that's what we're considering so far, is we're just going to look to start at systems where we don't explicitly consider the inputs to start, but that doesn't mean that our results are not applicable to systems with inputs. That means they could be if the system has inputs, but that these inputs are already functions of the state. And we'll have to eventually get to the case of general inputs, because not all inputs are functions of the state, like MPC doesn't really do that. So this is just where we're going to start to get an understanding. So then the next thing is autonomous versus non-autonomous systems. So we've simplified to some extent so far, and we've said, okay, I'm going to start by considering not having inputs explicitly on the right-hand side and considering the dynamics of either a system with no input or the dynamics of a closed-loop system where the input is a function of the state. And then the next thing is to say, okay, but we just said usually chemical engineering processes don't have the explicit time dependence, which is what this is reflecting. So we can also simplify even further at first and say, like, okay, I'm going to look at what we call an autonomous system. So the right-hand side is only a function of the state. So this is what we call an autonomous system. Or time-invariant. And then we have x dot equals f of tx. This one is the one we were talking about before. This is called non-autonomous. It has this time-varying dependence in the right-hand side. So we're going to start with these autonomous ones. And then we'll move back to non-autonomous if we get through enough stuff in the next several weeks. And if we don't, then Enrique can learn about it in his future. So the next important concept in discussing these differential equations. So when you do the Laplace transforms, for example, if you go back to the undergraduate stuff, the goal of doing those Laplace transforms is that you wanted to solve the differential equation because you want to be predictive. So yes, you can know how instantaneously the variables are changing, but unless you're able to make longer term predictions, it's not that helpful for you in control theory because you can only know like instant to instant, and what you really want to know is what's my longer term perspective? How will this system behave if this is the way I apply the inputs? So what we need to talk about then next for nonlinear systems is what is a solution of a nonlinear system and what are the characteristics of the solutions? So we can start to understand what are some of the benefits and limitations of different control designs for these systems in the end. So we're going to clarify what we mean by a solution. So by a solution of x dot equals f of tx, we mean a differentiable and we're actually going to require continuously differentiable. This means the derivative exists and is continuous. Function phi that maps from some interval I, which is the kind of the interval that the time is allowed to take. And it should also, I think, have cross r to the n to r to the n. So there's an interval I, the time can take, the x arguments can take some values, but this function overall, that's the solution here, is going to be vector valued. And then such that for all t in this interval, so this means for all t contained in I, which is the interval, then d theta over dt is equal to f of t comma phi of t. Oh, sorry, I did this wrong. I wrote here the argument of this side, but this is phi goes in here. So sorry, I did that wrong. This is mapping only from I to r to the n, so that then it takes the place of x in x dot equals f of tx. So phi is basically the function that you could plug in for x that would cause this differential equation to get satisfied.
Mm-hmm.
And that seems fairly, if you like kind of harken back to the old differential equations that you probably learned like 3 years ago or 4, then you can kind of vaguely remember like, oh yeah, that's how people define the solutions. They said basically it's that function where you plug it into both sides and it's both sides equal each other. But then I think something that is a little important just to point out here is some of the nuances of this definition. Like we are requiring that this function be continuously differentiable for all of the times in the time interval that you're mapping from. So there's actually an example that we can look at later, but maybe it's easier to just show now. So say that I do this dx over dt equals x dot equals negative sine of x. And x of 0 is 0. But then sine of x is defined like this. So the sine of x is defined to be 1 if x is greater than or equal to 0, and negative 1 if x is less than 0. So if we try to apply this definition here, then we say, like, is there a single function that is continuously differentiable for all of these i's? So in this case, we have the problem that essentially if it has to be continuously, this function has to be continuously differentiable. So if we take its derivative, which is, its derivative should be f of tx. Here, f of tx is negative sine of x, which at 0 has two different values. So that are not continuous at the initial condition x of 0. So the problem is we're not satisfying this because we needed it to be continuously differentiable on the time interval. We're starting at a point on the time interval where this would not be continuously differentiable. So then we say, okay, in this sense, there is no solution to this differential equation because fundamentally the right-hand side, there will never be an x that where we take its derivative will equal a continuously differentiable function because we know that this differentially, let me try to phrase this one more time. We say x is going to be some like function phi kind of is what we're looking for. We're looking for what function phi could we plug in for x where it would cause both sides of a differential equation. Wow, Wayne State University is calling me. So that where we plug it into both sides of the differential equation, that then what we get is that function was continuously differentiable. It satisfies the initial condition, and both sides are equal. So then we essentially one requirement of that is that this right-hand side has to be continuously differentiable at the initial condition, or else this is not going to hold. So then we see here that's not true here. The right-hand side is not continuously differentiable at the initial condition. So we say, therefore, there's no solution in this sense. And I think an important thing about this is to realize that there are senses of differentiability. So that senses of whether or not there exists a solution. So that as it turns out, like I think when I was younger, I thought like existence and uniqueness of a solution, like, the existence of that textbook on my bookshelf, I don't usually think of that in this like abstract sense of like, well, what sense do you define existence? I don't think of that. I just think like people have a definition of existence in their normal language, and I say that textbook exists right there. But then it's interesting, and I think it's even interesting from a mathematical perspective and from like a philosophical perspective and of what you could do with mathematics to take that step back and say like, that's interesting. So the reason I say that exists right there is because actually in my mind I have a definition of existence, and you have that same definition. So when I say that word to you, we think we mean the same thing. Say like, I could touch it, it's there. But then could someone like, there's a lot of things though that then we'll say like, for all intents and purposes, such and such thing is true. But then it's not exactly true, right? Because we added that for all intents and purposes. So I think there's a lot of things in life where we do like convey a sense of a definition to each other. And then it's interesting because in mathematics, you actually have to be precise about those definitions. So if I was to say, I don't think that textbook exists unless I'm reading it. So that textbook doesn't exist right now. Like if that was how I felt about it, because how sometimes we use words in a sense of feeling, like we're like, I don't feel like that's true, like, or whatever. But even if it is, like, I don't feel like it right now. And then, so there is like, then we're changing our definition, right, of truth. Then we're saying truth is based on how I feel or whatever. So in this, it's interesting because here we said there's no solution if this is the definition. But if I change the definition, maybe there's a solution now. If I said, I don't really care if it's continuously differentiable and whatever. Maybe now I make it so that there is a solution, but in a totally new sense. And so I think this abstraction is really interesting in mathematics because there's like, the more that I think people think abstractly in math, I think it makes it so that there are things that start holding across the board. Like there start to be properties that you can start applying to multiple things where you're like, I didn't think those were related, but now if you tell me that's an abstraction, you're right, those two are actually the same, or they're in the same framework. And one place I really see this is in real analysis, where it's really interesting because you know how you learn vector spaces in like linear algebra? People will say, here's the properties of a vector space, whatever, like you add two of the vectors in the vector space, they make a vector in the vector space, et cetera, et cetera, et cetera. Then they have all these things. It turns out that in real analysis, people have realized, well, there's other things that can do that. Like if I have an infinite dimensional vector plus another infinite dimensional vector, that makes another I should even go more abstract, a function of a certain type plus a function of a certain type is equal to another function of that type. Therefore, each of those functions of that type is in the vector space. And it's a function space. It's a space of functions. So it starts getting really abstract, but then it turns out that they all satisfy the same fundamental properties. So that if you base proofs off of those fundamental properties, you can start saying like, well, this does this, and so do the functions, and so does this, and so does this. So it's actually really helpful to realize that in math, you do need to make clear definitions of what do you mean. So like when we say a vector space, in my mind, if I think vector spaces mean using vectors only, then I like block out all the functions. If I say, no, vector space means this definition with all these like additions and like these following properties, now I say, well, this is in that space, and this is in it, and this is in it, and this is in it. All these things are in it. So definitions in mathematics are really, really important. So, and something that's going to happen just for you and Ricky, for you to know, I started looking at the PDE book on like PDE theory, and I saw that it says some things about like that sometimes existence for the PDE solutions can be more difficult, and people have looked at, oh, what about weak existence of solutions or something like that. So I think like it is really interesting to look at all the different ways people think of stuff. Mm-hmm. So, but yeah, I think training yourself to think that way is kind of mind-bending, but also really eye-opening at what more things you can do with science and mathematics. Mathematics is just amazing. So, any questions on this before I keep going? Yeah. Okay, cool. So, the next thing that we want to talk about, I'm going to skip this. So, now we're going to talk about some of the differences between linear and nonlinear systems. I was thinking about this last night, that I've always conceived of this part of the lectures, because as I mentioned earlier, I like was in this class like 4 times, and then I taught this class like 1 time, and then now I was reading it again last night and taught it to Enrique, this part of it already, and stuff like that. And then always you learn something new. So I was thinking about this concept of essentially the way that we've usually been talking about it is differences between linear and nonlinear systems is the way that I've always kind of thought of this. And I want to tell a little more about that. So differences between linear and nonlinear systems. So I want to clarify this before I speak on this. I don't think it is the most clear for me to phrase it in this way, even though I always thought of this, because this was why I realized last night. I was like, wait, oh, if I think of it a different way, it actually means something different to me. So what we're about to present is we're going to go through a series of things where linear systems have certain properties and nonlinear systems sometimes don't obey those properties, which I think is really more along the lines of linear systems are a very specific subset of the class of nonlinear systems, which happen to have some very nice properties. If you go to other classes of systems, you can find they have nice properties. Different subsets of the full class of nonlinear systems sometimes have different properties from each other. I think that's more the way to think of this, instead of trying to think like, well, there's linear and then there's nonlinear. I think it's more helpful to think like, there's a lot of stuff under the umbrella of nonlinear. There happens to be this special class of linear. There also happen to be many other classes. Happen that you only learned linear before, and that now we're saying like, oh, by the way, if you move away from that one class, there's a lot of other things that could happen because there's a lot of other classes of stuff and a lot more dynamics. So, the existence of solutions is something that we have not traditionally questioned in like an undergrad control class. No one said, oh, does the solution to this system of linear equations exist? And the only time you've probably heard of it is in the differential equations class they might have taken in mathematics. And then it seems like, why is anyone telling me this? This is all just theoretical math stuff where they're just telling this theory. And it turns out, though, it's very important for understanding these types of concepts for building good models. And so the question here is, does like x dot equals f of tx have at least one solution? And again, that would be in a predefined sense of having solutions, some sense you define. We've seen already that we can develop ones that don't. And so then we would want to avoid those. The reason being that if we're going to develop a lot of theory under certain assumptions, so essentially what that existence of a solution is doing is it allows you to place some conditions on your functions. So we said essentially that there's some type of requirement that I have a differentiable right-hand side. Or, no, a continuous right-hand side. Continuous right-hand side. So that's like kind of by making these assumptions on existence and the type of existence, there's some properties that come out of that. So what that does is then with those properties, there will come proofs in later time where we say, okay, if that's the sense in which we define a solution, then it has the solution is known to have certain properties. I can take advantage of those in making proofs. Then all my future results depend on the fact that I assumed that up front. So then if we make a lot of results, then we do want to make sure that the fundamental questions that we used to say like, okay, what am I talking about? When is there a solution? Help me define my class. Then we make lots of proofs. Then those hold back to this initial assumption. So we want to talk about when do those assumptions hold true. And so it doesn't just happen automatically, like because for a linear system, the right-hand sides are already pretty fixed. We don't have all this flexibility to be like, and then I thought of sine of x, or negative sine of x, or then I thought of x squared, or then I thought of this. We're like, no, it's ax plus b, and that's all you've got. So you've defined your right-hand side when it's linear. In this case, we're saying like, okay, I need to put more restrictions. And I need to understand because I want to classify when I have these solutions. Is this making sense? Excellent. Then there's this question about uniqueness of solutions. So this is also a really weird one. So this is the question of, does x dot equals f of x have only one solution? And this one I think makes a lot of sense practically to say like, I really am not interested in looking at models where if I was to apply mathematics to it, like integration, that if I did numerical integration, I have two different paths that I could take from there. That would be very problematic for all of science if we were modeling in those types of ways where we did not have unique solutions, and especially for control or like model predictive control, trying to predict the future, and then you say one of two completely different things could happen for the exact same initial condition and under the exact same conditions. So sometimes you're going to find in the future, like if we add disturbances, it makes it less obvious exactly what's going to happen because the disturbances are considered random. But if you have the same realization of the disturbance, you would like to be able to say, if that's the realization of the disturbance, here's the future trajectory. But if you couldn't say that, then you would be like, whoa, what is happening? I will not accept models that do that. So then this other one is continuity, so continuous dependence on initial conditions. This idea is that if you start at a certain initial condition, then you go a little different from that initial condition, you would like your solution to stay relatively close to the one it was at before, or if you have a slightly different parameter in your model, essentially with disturbances, your solutions remain similar to the one you would have got without that disturbance or with a different disturbance. Because or else, again, it just goes crazy if you're like, oh, like I thought, imagine the consequences of not having this. that it would be that you make your model predictive controller, you predict, your model's off. Then instead of your solution being close, which is what we bank on in MPC, the solution would be completely different because there was a disturbance. And then you would be like, like this is not predictive for real life, which is, there are always disturbances in real life. So that's why this is important. There's an issue of finite escape time. In this one, we have, so let's look at the linear system. So I guess I should clarify. All these things that we're talking about are things that we basically take for granted for linear systems because they already have a well enough defined right-hand side that they get a lot of nice properties. Now we're talking about, okay, what are problems that could happen in the solutions, essentially? Things we would dislike it if they happened, so that then we're going to start adding conditions to the right-hand side of the differential equation so we can bar those. What is finite escape time? So this is best shown through an example. So from like separation of variables, if this is your differential equation, it's a linear, small thing, single state. Now here's your solution in a general solution where I didn't like provide an initial condition, so I don't know what C is yet, but it's just your integration constant. So here, as t goes to infinity, x goes to infinity. So you had positive, essentially you have a positive eigenvalue here, so you would have a positive pole. There's a relationship between poles and eigenvalues. So in this case, you have a matrix on the right-hand side that's a 1 by 1. It has a positive eigenvalue of 1. So your solution has, you can consider it as having a positive pole, or it has this positive eigenvalue. The solution ends up being e to the t type. So as t goes to infinity, x goes to infinity, you can see that that means in the linear system sense, the solution is, or the system is unstable. Which just relating that back. So, but the sense of instability that we have when we feel like, oh, that's not good. I think a lot of mathematics is trying to characterize our feelings. Like, oh, that's not good. That's not good. And then we say, okay, in what sense is that not good for you? Well, as t is going to infinity, x goes to infinity. That is really what you mean. You mean it is not good. What you mean by not good is you mean the following property holds. Like, so then, so with this, it is also true though, that say t is 500, x is large, but x isn't infinity. So x is only becoming infinity as t keeps increasing. So, but now we can look at a different, where's the other example? The one with, okay, I guess that's a little later. Let me find it. Okay, I found it. Sorry.
Okay.
Oh wait, no, that's not it either. I can't find it. That's okay. Well, if we get to it, I'll tell you about it. But the basic point is, you can get solutions of nonlinear systems where, say the solution happened to be something like 1 over root x minus 1. If your initial condition was like below x equals 1, like say it was x of 0 is something, then as x goes toward 1, this is probably t. X equals, okay, here's the solution. X is equal to 1 over t minus 1. Say this was the solution of some nonlinear system. So then say that you start at t is 0, but you can see that as t approaches 1, this is going to infinity. So here we have the problem that x can go to infinity before t does. So we only had like a small amount of time before the state went crazy. So that can be a property of what nonlinear systems can do that you would not see that in this kind of system. Okay. Is it still good? Any question? Okay. Cool. Excellent. So here's another important point. It is about numbers of equilibria. So multiple isolated equilibria. So consider for a minute this system x dot equals ax. Let's talk about what happens here. So if you want to find equilibria, that's steady states. To find the steady states, you get 0 is equal to ax, because x dot is 0 at the steady state. So there's several things that will happen at this point. So this is a linear system. So either one, an example linear system, you have A is invertible or has full rank. That's all linear algebra stuff. There's also many other equivalent conditions to being invertible, full rank, etc., etc. Stuff about all your, none of your eigenvalues is 0, oh this, oh that, oh this, oh that. So they're all equivalent. But so say something's invertible, so that would be something like 1, 0, 0, 1. So I know this is invertible because it's full rank, because there's no linearly independent rows or columns. That's also equivalent to full rank. So many definitions are equivalent for this. But then, so if you try imagine solving this as a system of equations, equals 0, 0, say you just take this one. So this is full rank. Now what you get is x1 is equal to 0 and x2 is equal to 0. So when A is invertible, meaning it's full rank, meaning no linearly independent rows or columns, meaning none of the eigenvalues is 0, etc., 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 then as you can see here, for one example, there's one solution. Case 2, it's the 0 solution. So nothing else will satisfy this. Case 2 would be something like 1, 0. So this would be like not invertible. 1, 0, 1, 0. Okay, say it was this. So this is not invertible because you have linearly dependent rows and columns. So what ends up happening is that you get x1 is equal to 0, and then you get x in the second row when you multiply it out, you again get x1 is equal to 0. So in both cases, if x1 is 0 and x2 is anything you want, you solve this equation. So regardless of the value of x2 here, it always multiplies 0 in the matrix, so it always equals 0. So the second equation isn't needed. So you have linearly independent equations. The second one is not really relevant because it gives you no new information. So what we say is that we have a null space. So Enrique, how much did you learn about all the when I started grad school, the first class I took was like advanced linear algebra. Have you taken linear algebra since the first class on it?
In undergraduate, you mean?
In undergraduate,
yes,
yeah.
I have taken.
You've taken it again?
You mean with your professor Lee's college?
Did you take it in mathematics, or did you take it in chemical engineering, or in what sense have you taken linear algebra?
Mathematics.
Oh, okay, cool.
Mm-hmm.
And then you haven't taken it again since then, right?
No.
Okay, cool. Yeah, so for me, when I first started this graduate level course, it was very, very hard because it was like the first time anyone had ever, except for the advanced control class that I'd taken like as a senior, and then which was all this stuff, and so I like, oh, I got something, but a lot of it was just like, oh my goodness, I don't know what's happening. I was only a senior, and then but then it was really hard doing the linear algebra, but I'm always really glad I did. So at some point, probably you should take, or I should tell you. Because then there's a lot more that could be said about this, like about null spaces and all these things. But I'll tell you about that later.
Okay, thank you.
Sounds good. So here we have this, and then so x1 is 0, and so we have like essentially if you do anything where you have the 0 and a, where a is in the set of real numbers, this will satisfy this equation. Because any number here is fine. Then, but these are connected. So any vector in this line will be an equilibrium in the sense that it will cause ax equals 0. So, but these are multiple connected equilibria. And we say connected because you can see A can change to any number, like it's not discrete. Any number A in the set of real numbers will cause this to hold true. So A1, A1.01, A1.001, A1.00001, etc. Like anything you can imagine, they're all an equilibrium, so they form an equilibrium subspace, but it's connected. Because you would say each one of those, regardless of how infinitesimally different the A's are, is in that equilibrium subspace. All of those are equilibria, but they must be connected because it's like no matter how infinitesimally different. This is in direct contrast to something that can happen. So this is like the two cases you can have with a linear system, just because of the way matrix algebra works out for systems that behave like this. This is the extent of what can happen. So again, this harkens back to the fact that when we're talking about linear systems, we have very special properties of those systems that people have long exploited and worked with because mathematically it's very well characterized. So essentially what's happened is that then people try to find ways. This is also true. You might wonder, like, well, why does everyone always model the world with linear systems then? It must be the way the world is modeled. I think it's really because matrix algebra has very, very well characterized properties that can do a lot. So I think people are like, can I make the world linear? It's so nice when I can. So I think that's why it continues and persists, is because matrix algebra is just fantastic. And so people want the world to be linear. So then they make it linear and by various approximations. And then that's why probably it's like, well, shouldn't this describe everything? Well, it doesn't. As you saw, like chemical processes are almost never modeled for real with linear equations, but under certain circumstances we have been able to show that it should work, and then so people said, well, I like that better, and then they do. If it should, under certain circumstances, I want those circumstances. So then imagine this, though. Now we're going to nonlinear, x minus x cubed. So if I factor this, so what we're looking for is 0 equals x minus x cubed. So we're looking for equilibrium. We're saying what values of x will cause this equation to be satisfied. So we can do factoring, 1 minus x squared, and then factor again. So this goes back to like quite some while ago. You can see how, okay, that's equivalent. And then if you do the factoring stuff from a long time ago, then these things all cause this equation to equal 0. So you say like, oh, okay, look, these are actually multiple and isolated. They're not connected and there's multiple. Each one is distinct and discrete in the sense of the following. Here is 0, here's 1, here's -1. So each of these is an equilibrium. So if I start here at x is 0, I will never move off. I will remain at x is 0 forever and ever and ever and ever, if this is the perfect model of my equation of no disturbance in the center. Same thing if I start at 1 and I'll never move off. If I start at -1, I never move off. But if I start in between them, I either go to it or I go away from it. So I have not really checked on this one as to like which direction each of these would go. We could probably try to figure it out a little bit. So like, say that I start, okay, so here would be the way you would sort of see. So either I go to -1, if I like start over here, either I go to -1 or I go away from -1, and we have to see. So then you would say like, okay, so x dot is equal to -1 times, oh, let me try -2. So I'm going to start below -1. -2 times 1 plus 2 times 1 minus 2. Is that right?
Mm-hmm.
How about now? 6. So x dot is 6, so x is increasing when I'm at -2. So I guess I'm going this way. So what that probably means is that this is how the solutions go, most likely. The reason that I say that is that I guess I don't know that for sure. Mm-hmm. We would have to check all the other ones. Right. We only really checked this one to see. But pretend for a minute it's this. I'm not sure. I haven't checked. But this is then getting to the question of stability. So you know how you cover stability in undergrad control, and then you say like, does the state go to the origin, or like what happens when it's perturbed. So if you want to look at stability, some of the questions are, is you only focus on equilibria in nonlinear systems? Because say this was true for a minute, just pretend. I don't know, I haven't checked. But if, for example, every solution starting at 0 stays at 0, and every solution infinitesimally off of 0 goes to like 1 if it's on this side of 0, goes to -1 if it's on that side of 0, then 0 is an unstable equilibrium. But this system is not unstable because the solutions are going to -1 and 1. So there are stable equilibria. We cannot say anything about this system because that doesn't make sense, because there is no sense of stability when you have multiple equilibria. Like if you just say the system is stable or the system is unstable, that doesn't mean anything. And equilibrium can be stable or unstable, meaning that trajectories that start infinitesimally small from it either go away from it or go to it or do other things like stay around it, or you have to also define stability actually as well. So that is one thing to note about nonlinear systems. The next things, okay, so we already did that. So other interesting stuff that can happen. Wait, did I already do this? What is this? What is this about? Oh, okay, that's just another example. If you want to think about an example, I'll just do this one thought-wise instead of writing it up. Another example of stable and unstable equilibria would be if you have like a pendulum and you imagine like balancing it 100% straight up, no disturbances, you manage to get it in that one position where it sits. And then if any disturbance, you start slightly off to either side, it goes down. If instead you start it like this, now you move it slightly over here, it goes back. Slightly over here, it goes back. So unstable equilibrium, because you could make it sit there, but any disturbance is going to kick it off. Stable equilibrium, you can make it sit there, but every time you go slightly off, it draws itself back, at least within a certain range. But that range isn't infinite either. Like, because, for example, if you started it here, then it doesn't just go there. It stays here, unless you kick it off. So there's not a sense in which, like, that's just attractive or something.
Mm-hmm.
There's this interesting notion of what happens in linear systems called limit cycles. So,
But a pendulum is a stable or unstable system. Can we define this?
No, because it has
Undefined.
multiple equilibria.
Okay.
So then that's like what we have to be really rigorous about in all, like anytime that we're talking about stability in a paper, we will never say stability of the system because it's completely undefined.
Mm-hmm.
But you can talk about stability of an equilibrium point. So it means if you have two states, by the value of x periodicity in your solution, it could be true that you have periodicity in the solution for a vector. So this x doesn't have to be something you can plot here. If this holds with a vector, so you have a vector, every t time units, all the entries in that vector become the same. Like you have x1 evolving in time x2, x3, x4. They're all evolving, and every time period, all those ones become the same in that whole vector. Oh, and then it's periodic, it's oscillating according to the mathematical definition of how we have to find that. Well, it's not very easy for me to try to figure out in my mind and imagine what it would mean for like a 15-dimensional system to have an orbit. I feel like I cannot even like figure out. I can figure out like, okay, I could check whether or not this definition's met to say is it oscillating. But then this thing about this periodic orbit, okay, so if you have two states, you can do parametric equations. So in parametric equations, what happens is basically each one evolves in time. So you have it's a function of time. Then you plug in the time, you get the value of each state at each time. And then instead of plotting each function of time, or each state as a function of time, you say, oh, at this time, these two states are the same, so I'm going to plot them in the state space instead. So like here and here could be very different times, but then we just plot them here. So if you're getting something that's like this in the state space, and if what's happening when you get this is that this is just going on and on and on and on forever, so like every time t, here are the values of x1 and x2 together. Then, okay, you go here, you go here, you go here, you go here, all the times go by, and at another, after a period t, you have the same values again. Now you can see what that means like in orbit, but how that fundamentally relates to the concept of oscillation. So that's why I think it's good to do that, because or else it's kind of confusing. Like, what's an orbit in like 15-dimensional space? What's that even? So the interesting thing about this do you need a break for like 5 minutes? Is it still okay, Enrique?
No, it's okay.
It's okay? Okay, cool. Then, so we're going to talk about when linear systems do this, and just to kind of relate back to like what have you seen to this point, and then to say like, oh, okay, and by the way,
just a brief question. These limit cycles must be a cycle, or just need to be a periodic function, like would be a quadratic function or anything here, or if the path would be like this still is a limit cycle?
I think it would be a limit cycle if it's periodic in the sense of like this. So it's oscillating, but then like if the whole vector was oscillating, like this one is.
Mm-hmm.
So it doesn't have to be in 2 dimensions.
Okay, but it could be any shape.
Oh, yeah. It doesn't have to be a certain shape.
Okay.
Yeah, that's a good question. It can have very weird shape.
Mm-hmm.
Some shapes that are in the book are like some stuff like this kind of. Things like that.
Okay.
But they're just like following this repeatedly, essentially. Like in state space, this happens to be the way it looks.
Mm.
But then look is not really the mathematical definition here. I think people recognized a pattern and realized they wanted to characterize this pattern mathematically, where the pattern was it goes on some orbit and stays there forever. But then that orbit just is like after a period. So if you look at any point on this orbit, then after so much time it will be here. But then if you also look at this point, after the same amount of time it will be back here, but it's okay that it wasn't a circle.
Okay, thank you.
Yeah, good question. So then here is like an example of a linear system. Negative x2 dot is x1. So in this case, so here's x10 is x10, x2 of 0 is x20. So here's the initial condition. So we have a system of 2 differential equations. Therefore, we need 2 initial conditions, which we have. So then it turns out that, you know how the way that anyone does solutions of linear equations is even as weird as it was. I think when I was in undergraduate and people showed me how to solve linear equations, you know how some of it is like, if it has a term like this, guess that it's a sine and then check. and see, you know, that's how they teach it, right?
Right.
Yeah. And then when I was in that class, I was like, they can't be serious. There must be a more systematic way. And then so it's worse for nonlinear systems, right? Then it's like, I have no idea. You can't guess. Just try it. Integrate it numerically. Figure out what happens. But then, so in like the guess and check world where, because apparently like people don't, my impression then is people don't really know how to solve differential equations. They figured out a few of them, like, oh, if it's like this, sometimes I guess this, it works. So it's not really super rigorous compared to like really solving stuff, but mathematics is a lot more interesting than we like to give credit sometimes. So then it turns out if you like go and guess and check world, or maybe someone knows a more systematic way to do it for this specific class of systems. I think actually linear systems actually do have so I'll take it back. Linear systems actually have an analytical solution that you can put as a much more rigorous one, but I think those were ones with like forcing functions and stuff. I think there are more rigorous ways to do it than just guess and check. So, but for some reason, that's how we like to teach it.
I don't think they always have an analytical solution either.
I will neither confirm nor deny this now because I'm not sure either. I forget. So, if this is what these things are, so basically you use your initial conditions and then you get these angle and this R. So essentially here's the solution. Someone figured that out. I don't know how. I don't know if they had a good way or if they guess and check. Maybe one or the other. So then what happens is it turns out that if you were to plot in the like space here of x1 versus x2, that if you plot this thing and you plot the values of x1 and x2 against each other as time changes, that you end up getting these periodic orbits, where the orbit that you're in here is going to depend on your initial conditions, because this is setting like the radius of the orbit, so like a different initial condition leads to a different orbit. But then something about these is so this is for this linear system. Two things. One is that this is not structurally stable, and I'll define that in a minute. It's not structurally stable, and furthermore, the amplitude of the oscillation depends on the initial condition. So let me define not structurally stable. So imagine that we take the exact same thing we just had, but we add this very, very teeny tiny perturbation of minus epsilon x2, where epsilon is like so tiny. So there's almost no difference in this right-hand side compared to what we had before. Epsilon is so tiny. Then now what turns out is you can go back to the eigenvalues here, which would be 0, 1, 1, negative epsilon. So before it was 0, 1, 1, 0, and that ends up giving eigenvalues that show you that you have this oscillatory behavior, or that if you were to find the solution, it would give those the eigenvalues that give oscillatory behavior. So now you have 0, 1, 1, negative epsilon. So what happens is if you were to find the eigenvalues, then it would no longer give you ones that are on the imaginary axis, so that you don't get just oscillation anymore. You would get a solution that actually, like, either, in this case, I don't know if it goes away from the equilibrium or if it goes toward it. But things like this would happen. So either for negative epsilon or something like that, I'm not 100% sure. Like, you could start at a condition. So before you add this epsilon, you could be on this rotation. Then you add epsilon and maybe it starts doing something like this and goes down to the origin. Something like that. This is not 100% exact because I didn't really check the eigenvalues here, but it will be something like this. Like it will stop the oscillation just by any infinitesimal change that you do here changes the eigenvalues. And the eigenvalues are what's governing whether or not this is periodic or not. Does that make sense, or should I try to derive that a little more on the board? Would that be preferable to derive more, or it's okay? It's okay.
Yeah, I understand it. I just don't really get where you get that matrix from.
Oh, good question. So this is x dot equals this x.
Okay.
So that came from this. Good question.
This epsilon we can think is a small disturbance.
Yeah, exactly. That's exactly true. So it's essentially that this is saying assume that my model was actually slightly off and this was the real model, but I was really close. Then it says if that's true, then the behavior you're going to get is completely different than what you'll predict.
Okay.
So that's how this is not structurally stable. And that's also why I think the book says you're going to very rarely ever see a linear system actually on a periodic orbit, because they're not structurally stable. So like the likelihood that you're going to have any real system that really has these eigenvalues on the real axis and the full out system is 100% modeled by that as well, so that you have no disturbance. The likelihood of that is so small that you'll probably never see a linear system really in a periodic orbit.
Okay.
So then if you want to see any system in a periodic orbit, it probably has to be a nonlinear system, because those have structurally stable periodic orbits that can be achieved for certain systems. So the idea with that would be, like, say that there are some nonlinear systems where you'll have like some orbit, doesn't have to be like a circle, it could be some weird ellipse or some other orbit, like we were saying, some weird shape that's periodic. And it can turn out that these are like attractive in a similar way, not the same way, but you can think of it as being in a similar way to the way the origin can sometimes be attractive to solutions. So it can be like the solution starting from near this, go to this, and go into the orbit. And then that can happen for like various initial conditions around it. So then it can be, and then if it can be structurally stable. So here this oscillation is not dependent on the initial condition. So that was two of the things we said. In the linear case, it was the oscillation amplitude is theoretically dependent on the initial condition, meaning that I would have different like amplitudes of my oscillation, which were reflected in these different orbits, if I have different initial conditions. But then for a nonlinear system, it can be true that I have like an orbit where I start at different initial conditions and the solutions go to that orbit instead of like something else, instead of going to a new orbit. And then, but the other thing is that it's also structurally stable in the sense that there are some systems for which if you add a small perturbation on the right-hand side of the nonlinear system, so it's slightly off, maybe it will go to some new, it'll make some new orbit. But like maybe it's like close, it's not exactly, but it's another orbit. So it didn't just say, never mind, no orbit for you if you can't be exactly 100% right on your right-hand side. It said, oh, there's still an orbit. Maybe it's not exactly the same orbit because fundamentally your differential equations have changed, but there was still an orbit for you.
So the disturbance would determine like kind of like the shape of the orbit.
Yeah. So essentially, I think this brings up a very good question. So something that should be thought of is say that I go back to this one down here. So x1 dot is this, x2 dot is equal to x1 minus epsilon x2. So if I don't have this, I have one differential equation, and the way that the system changes over time is governed by like these equations. So there's these equations. If I add any disturbance, even though we say, well, it's very similar, but fundamentally it's actually governed by a new set of differential equations. And it turns out that for linear systems, a lot of things can be proved about like similarity, because like you can look at the eigenvalues and you can say like, okay, so for linear systems, the eigenvalues are what determine the solutions. Essentially, you get solutions to linear systems of a form like e to the lambda 1 t plus like c1 e to the lambda 1 e plus c2 e to the lambda 2 t. This is sort of the form that you would expect for a linear system in general, something like along those lines. That's not exact, but something like that. So the eigenvalues are actually very important in determining how the linear system behaves, because if these are both negative, then both of these terms decay over time and x will go to 0. if one of these is positive, then even if this one decays, this one is always increasing. So then it's unstable. So that's like the idea of, you know, how we say, so it actually turns out the poles are the eigenvalues. So when we say that you have a positive pole, then the origin is unstable. So positive here, you can see it will go to infinity. Then if it's 0 here, you can see how what happens is it just is C1. So you can see how that's like very structurally very different. And there can be other things. Oh yeah. So if it's, so when we talk about the eigenvalues being on the imaginary axis, so if it's 0, so the imaginary axis is like a plus, so if you have a plus bi, so this is a complex number, then if you're on the imaginary axis, you have just the bi part. So there could be a b, or b could be 0. So if b is 0, so that lambda 1 is 0, then you can see that if both of these lambdas are 0, then x1 is just c1 plus c2 is just a number. But if they're both like, if they're I, then it's c1e to the bit plus c2e to the, I don't know, I'm just going to b1it, I don't know, something like that. Pretend that your eigenvalues are both on the imaginary, or I guess negative bit, the complex conjugate. Then it turns out you can rewrite, so you know how there's that Euler rule, like e to the, something like ai is equal to something about cosine and sine getting multiplied, getting done. It's like an Euler formula. I'll have to, let me see. It's like Euler notation. Euler notation. What is that? Imaginary. Okay. Let me see. Oh, that picture says it. E to the I theta equals cos eta plus I sin theta. Okay. E to the AI is cos A plus I sin A. Mm-hmm. Excellent. So you can see that then, and then if you add the complex conjugate, so this will be, so if you start adding complex conjugates, what starts happening is you start getting these, essentially your end solution has cosines or sines in it. So that's where we get oscillation from having eigenvalues on the imaginary axis. But then what this says is, so the eigenvalues are so important. So then if your eigenvalues of your system are on the imaginary axis, which is the case when we do not have this perturbation, this says you've got an oscillatory solution. It says your solution has cosines and sines. If we add this disturbance, what happens is the eigenvalues are no longer on the imaginary axis. They're either like positive or negative. So then the solution is either going toward an equilibrium or away from an equilibrium. It's no longer just oscillating based on the initial condition. So then that's why we're able to make these conclusions with these linear systems about those properties. Good question. I don't know if that even answered a question or if that was just some new information.
A little bit of both.
So yeah. So it turns out that the nonlinear systems, for some of them, so you don't get like periodic orbits for every nonlinear system, but for some of them, you can get it so that they have a right-hand side that overall it will cause, like, there can be periodic solutions to nonlinear systems. And then it can turn out that for some of these, if you add perturbations, that now, even though the right-hand side's different, it makes some oscillatory solution still, even with the perturbation. Maybe not the same oscillatory solution, but it happens that that solution remains oscillatory.
Okay. This is only for nonlinear systems. For linear systems, if your function is periodic, it will continue to be periodic even with disturbance.
No, like for the linear one,
for the linear system,
the only way to get the periodicity is the way that we just described.
Oh, okay.
Yeah. So then linear systems have it so that they could theoretically, under very specific conditions, get isolated periodic orbits. Or I guess get periodic orbits. I don't know about isolated. Get periodic orbits that depend on the initial conditions and are not structurally stable.
Okay. Mm-hmm.
So if you want, so the book says that actually people have tried designing something about like oscillations that they needed in circuits with like nonlinear systems in some sense. Don't quote me on this. It was something like this. You would have to read the book. But it said something like that because it said if you wanted to get one of these with a linear system, the disturbances will always make it impossible. But if you try to figure out a way to do it with a nonlinear system, because the orbits can be structurally stable, now you can actually achieve some new like technologies. So I thought that was cool. I was like, oh, mathematics is the best. It enables us to do so many things. And then, okay, so here's a weird example about the lack of existence of solutions. So here is an original equation. So it turns out that this is one of those ones that's separable. So you can see by doing separation that you would be like, oh, okay, here is a solution. If I plug this into the right-hand side, I'll see that I can say like, oh, okay, if I do the derivative of this, so 3/2 2t over 3 to the, okay, I should not do it like that. Okay, so this is 2/3 to the 3/2, t to the 3/2. So it will be 2/3 to the 3/2 times 3/2 t to the 1/2. Okay. And then you say, is that the same as putting this on the right-hand side? And then you would say, like, okay, so if I have 1/3 of this, so it's 2t over 3 to the 1/2, I guess. So 2/3 to the 1/2, t to the 1/2. And so this should turn out to be the same. Does that seem right? So I guess this is 2/3 to the 3/2 times 2/3 to the -1, so -2/2. And then so it turns out the same. So you can say, okay, this is a solution. And does it satisfy the initial condition? That's the other question. And so you say, yes, if I put 0 in for t, and then I put 0 in here, I get x is 0. It, okay, satisfies the initial condition, it's a solution. So then the other problem, though, is that if you also do x is equal to 0 for all time, so this would be, oh no, x of t is equal to 0 for all time. So then now it's also true. 0 is equal to 0. So if I start at this initial condition, and that also satisfies the initial condition. So the problem has become that now I actually have two solutions that both satisfy the initial condition. And that's just really weird. Sorry, I just want to get these in order before I forget. Okay, so then that's something you probably do not like very much. So then that would be a problem of lack of uniqueness. So like I say, if this was your actual equation and you imagine trying to deal with that in a predictive controller, where you take a measurement of your state and it's 0, and then you say, well, what was it in the future? And you're like, I don't know, it could remain at 0 or it could become something else. I don't know. That's so crazy. So one more interesting thing about the nonlinear systems. So like I say, I think it's good to not necessarily think of all these things as like, well, there were linear systems, and now there's nonlinear systems. I think it's better to think of it as I'm broadening my horizon as to the types of phenomena that may be seen in mathematics. It happens that I have focused on a very specific class before that had very nice properties, but now I'm realizing not every equation I could come up with as a model of physics will have those properties, because I can see there are many simple examples I would make where those properties don't hold. And so that tells me that I need to do something and figure out what are the general things that if I start imposing them will allow me, even for general classes where I didn't have to pull one up and say like, well, what about for this one? What about for this one? What about for this one? Like, you don't want to have to do that for every one of them. You want to be able to speak generally, but right now we're just trying. I think this is kind of like something I was telling Enrique the other day. I was telling him how I think the papers in our group right now are very much either invention or discovery type papers. And so the invention ones, I think the one you're working on is more like an invention one, because I'm like, okay, I know what we want to do. We want to say, here's the new, like, Lyapunov function, or here's a new stability region. I'm going to, every time that I hit it, I'm just going to start applying h of x instead of requiring an omega rho e or whatever. And then, so that's something where we're like, okay, I see a problem, I see a solution, therefore, invention, I'm doing the following. to prevent that. It does require me to know theory, and I will have to do some proofs, but I know what I'm doing, and I know why I'm doing it, I can back it up. Then there's like the discovery side, which is like along the lines of some other work that we're doing. So like I'm looking at optimization-based design of materials. And so on that project, then I'm like, how would you design a material with optimization in a very general fashion? That will take some like sort of discovery of saying like, what are some approaches that we could try? Which ones work? Why not? And also the cybersecurity of control systems is having the same thing right now. What exactly are we talking about when we say cybersecurity of control systems? What are the attacks that could be performed? How would we prevent those? Those kind of things. So that's on like the discovery stage. So I think this part of the lecture is very much the discovery stage of saying like, I'm not trying to say like, here are the differences between linear and nonlinear, but sort of doing that exploratory. Like, what are some of the weird things that could happen that you never ever thought about in your life so that then you can take action against them? And then, so this is also one more interesting one. So this is called a bifurcation. So if I give an example, I think this thing is easiest understood through an example because my notes say a topological change. I actually have never studied mathematical topology, so I don't think I could give you a very rigorous definition of what that means. But I think through an example, we can see the, like, what are we basically saying? So if you imagine that you have, okay, another pendulum thing. And also, I think the reason why a lot of these examples, so some constant angular momentum, some angle that you can, so it's like those ones, do you ever do that thing, you know when you do it? The things that, okay, when I was a kid, there were these things that, like, would hit each other if you, like, kind of, like, swing your wrist, and then they would, like, swing, and the little things would, like, hit and hit and hit and hit, and I don't know.
The kinetic balls, like, where there's, like, 4 or 5 balls, and you take one, and so,
no, I mean, it's like a...
It's a toy,
like,
right?
Yeah, it's a toy. It was, like, when I was a kid, and it has this, like, it has, like, a stick, and then it has, like, 2 sets of 2, like, clappers with a ball on each end. And then you, like, give your wrist a little flick, and they, like, hit each other and go around in circles.
He don't know.
yeah.
That's all right. Well, can you imagine, like, you take a pendulum and you do this?
Right.
And then how will it behave when I do this with a pendulum?
Would you keep applying that force, or just like...
Yeah, if it keeps going like this, constant, so constant angular momentum.
Okay.
This is just to get a sense of, like, what am I talking about physically? You know, when you, if you imagine having something on a string, like when I do with my keys.
Right.
So then, with regard to the angle, you know how, like, the angle, if I was really able to do this right, the angle that the big key is taking would, like, remain the same.
Right.
If I was doing constant angular momentum, but if I just, like, drop it and give 0 angular momentum, it just is flat. And so that's kind of what we're talking about here, is that, like, spinning motion. x1 dot is equal to x2. x2 dot is equal to g over r alpha cosine x1 minus 1 sine of x1 minus beta x2. Beta has something to do with friction. I didn't figure out this model. This came from my notes. So I couldn't tell you all the things about where all these terms came from. I would have to look back at a physics book to try to figure that out. But it's okay. I think don't worry about that point, because just assume this model's right. But then here we have r omega squared over g. So we're going to call this a bifurcation parameter to show what's going on here. So bifurcation parameter. So then let's talk about, so I think it will become clear why we care about this parameter in a minute. So if we try to look at the equilibria of this system, we would say that it's for 0 is equal to x2 and 0 is equal to g over r alpha cosine of x1 minus 1 sine x1 minus beta x2. So then we see, oh, okay, well, x2 is 0 from the first equation, so this goes away. So what I get left with is that I'm trying to find the solutions of 0 equals g over r times alpha cosine of x1 minus 1 sine x1. So then if I try to say like, okay, well, there's either this term is 0 or this term is 0, or both, I guess. But then it's just, I don't know how interesting that is. I don't know if both can be 0, actually. We'd have to see, because these require two different things. I guess for both to be 0, both pieces would actually have to be able to be 0. So we're going to say, here's the options. Let's look at if these can be 0. So the cases where sine x1 is 0 is stuff like x1 is equal to 0, pi, etc. So that would be the case that 0, pi, those are the ones that we already said for the pendulum, where we said, like, I guess I could, like, keep it up, I could keep it down. Okay, so I can either apply no angular momentum, or is that true? So I guess I can, somehow I can get one of the equilibria to be down here. I could get one to be up here. And then the question is, are there any other ones? I don't know if I do 0 angular momentum, then this says, okay, yeah, I have 0 angular momentum. This says negative g over r is equal to sine, no, 0 angular momentum means alpha is 0. So it would turn to be negative g over r, 0 equals negative g over r sine x1, and it would give us these. So if I do no angular momentum, I'm back at the case from before, where either I can be fully up, fully down. I'm not spinning it, I'm just letting it go. So then we said we can visually understand there's one up, one down. But now if we're spinning it, we can say like, okay, my angular momentum is going to affect whether or not I actually have another equilibrium. So because here cosine of x1 is equal to 1 over alpha. So cosine has a range. So if, for example, alpha is 0.0001, then cosine of x can never be like 1,000. So that means that I didn't add another equilibrium. But if cosine starts to get in the, if cosine of x1, if this alpha gets in a range where now the right-hand side is within the range of cosine, we do actually have more equilibria. So this says that for certain values of alpha, like if alpha is less than, so alpha less than 1, then 0, 0, and pi 0 are the only two steady states. So I'm rotating too slow to make a new steady state. If I rotate too slow, we can think that that pendulum's kind of going to swing a little and go back to the origin. I'm not providing enough force to, I'm not providing enough essentially like centripetal force to get it to make its own new equilibrium that's not at 0. And then, but then if I get it so that alpha is greater than 1, now cosine of x1 is less than 1, because 1 over a number greater than 1 is less than 1. So now I'm in the range of cosine. So then now I actually have a new steady state where x1 could also be equal to plus minus the cosine inverse of 1 over alpha. So this means that, and we know that that happens physically, that when I start applying enough rotation, I know that I'm going to do that thing where the ball of the pendulum is going to be out here, and I'm going to just see it keep rotating out there, and I'm not going to see it like kind of drift back to the equilibrium, because I know that I can apply enough force to get it to go out. So I actually have fundamentally changed the number of equilibria that I have for this system by modifying this parameter alpha. So that's what we mean by the bifurcation, is that I have very significantly changed the actual features of this solution. So it wasn't just like, oh, I changed the, you know, like, oh, I made it so that I had a slightly different initial condition or whatever. Like, this was like, no, I actually changed, like, there were equilibria before, and now there is a whole new equilibrium that the state could go to. And I have to analyze its stability and then all these different things. So it was a very large change. So it was a bifurcation parameter, because as this parameter changed, the way that my solutions look has significantly changed. That makes sense? Cool.
The chemical engineering have you, I think it's not often to have this kind of bifurcation characteristic.
I think I've seen this in papers or people like analyzing the dynamics of CSTRs and stuff with like different inputs, but don't quote me on that. But I think there are things, but I think I would maybe not. I don't think I ever think of it in these terms really, but I think it brings up an interesting point of analysis where you can say like, I realize that if the following is true, then these are the solutions. But if this is true, then these are the solutions. And I would think those things could happen in chemical engineering, but I don't really have a good sense of that, so it may or may not be true.
Okay.
Yeah. Yeah. And I think that brings up a good point, though, as you ask, Enrique, which I'm just trying to emphasize this because I know the first time that I took this class, I thought it was, like, very overwhelming, like, as the amount of new information and, like, whoa, I never knew systems could act like that, and whoa, I felt like I was being told that, like, everything about mathematics was, like, shattered in some way. But I just want to be clear that that's not what's being said. These are actually, and these are not, I also think I thought, because I was young and naive, I think I thought that what I was being told was that, like, well, linear systems, they're just crazy. Look at all the things they're doing or something. But that wasn't also the point either. I think what I was being taught was analysis tools. And I think that that's how to understand these beginning things. I was actually thinking about this even while I was walking here. So I was like, wow, what's the point of learning these things, for example? Because none of this is like a rule, right? All of this is, sometimes this happens for some systems, depends on their dynamics. I couldn't tell you if one's going to do it ahead of time. It's weird. Then I think, though, what it's doing is it's helping you, because what you're going to have a lot with the nonlinear systems, something that will happen is you're going to have to understand why your results happen. And so I think yours will be mostly, for the most part, relatively straightforward for the CSTR, and we'll see if we get any further than doing stuff with that model. But I know for you, Enrique, we're eventually going to be having all kinds of like complex things that are going on, and we're going to want to understand like why things are happening. And I think that by understanding and seeing like, wow, a lot of things can happen, but then not just understanding like, here's something that could happen, but why? Like how I went through and said like, here's how you could figure out that was going to happen. Even though like you might wonder if you were just spinning that pendulum and say like, I should be able to model this in a way that has those multiple equilibria. It has some equilibria with one thing and then has some with another. And you say like, well, could that be mathematically captured, and how would that get captured, and what is it that's changing to do that? Then you can say like, well, I know when I change the angular momentum, it does that. So does this equation capture this? Well, you say like, oh yeah, it does. Look, as I change the angular momentum, I actually fundamentally change the nature of the solutions. And I think that's going to be a very valuable skill to be able to like analyze these small scale models, because what they do, even though like I'm never going to model a system like this in industry, but what it's doing is it's teaching you how to think about the dynamics, so that then when you get a real or a bigger system, you can maybe, a lot of times what really helps with like systems theory is to take a very small example, just like we did here. I'm going to say like, okay, let me take a small one and see if I could replicate that kind of phenomena and see why it happens in the small one, and then see if I can take it to the large one. Because then I have an idea of why before I just start like shooting in the dark to be like, I don't know, this system's so big, what might be going on? But if you take the smaller ones, a lot of times you figure something out and you say, oh. And then you relate it back to the dynamics like we did here, like, oh, if that happens again in the bigger system, I can see the same thing. So I think that's like a lot of why we do this and how to understand. Does that help? See what's going on? Okay, cool. We only have 5 more minutes, but maybe if you don't mind, I'll just keep going for those 5 more, and then. Okay. You're sure? Do you need to put more money in the parking meter?
No, I have a parking garage to it. So.
Okay, cool. Then oh yeah, okay, just a few. Oh, that's right. Okay, let me try to get through these last 2 pages then. So then I think this is also one of the great challenges of nonlinear systems at this time, is that we don't really have, at this point, super good ways of being able to like make generalized predictions. So when I want to say like, so when I talk about cybersecurity, for example, we have a chemical plant model and it gets cyber attacked. And I'm like, I don't even know what to do about that. Like if I was to take really like the model of a whole refinery, and then try to be like, okay, figure out a cyber attack for that and tell me what it's going to do. I feel like that's like overwhelming. Like, how many differential equations is that? And how would you even figure out how to attack that and all these things? But then, like, so what we're doing is we're taking really, really simple examples like the CSTR and saying, like, okay, what attacks succeed? Why do they succeed? What does that tell me about nonlinear systems and how cyber attacks work? So then I can build to the next thing. So then it is, small scale examples do turn out to be pretty valuable. I think it's also good to recognize that they're not real. And to not try to fool yourself and think, oh, because it happened here, then it will happen like this. But whatever you understand about mathematics from doing the simulations is what is important. Simulations themselves are not real when we do CSTRs. So, what's this one about? I think I did that one. Oh, chaotic solutions. So this also, I was like, whoa. Chaotic solutions. Wow, that sounds fascinating. What is that? It's not as cool as it sounds. Basically, it just means like, we didn't really know what's the solution. Kind of varied over time. Wasn't really periodic. Just sort of something. It says like there is infinite period. That means basically there's no period. So it's just something. Just something that wasn't really characterizable. Chaos. Yeah. Domain of attraction is a very important point. And this is super critical for control. So this is going back, again, if you compare with the linear systems, you know how when we have x dot equals ax? So so let me just give a definition. It's probably the most relevant to Enrique. So A is Hurwitz. What this means is the real part of the eigenvalues is less than 0. For I is 1 to n, so for all the eigenvalues. So every single eigenvalue is negative. What that means is, for a linear system, if it has negative eigenvalues, it would have negative poles. So then if you think of that, when you learn about something that has negative poles in undergrad control, then assume there's no control here, that it's just pure out dynamics. Starting from any initial condition anywhere in space, the closed loop state goes to the origin. That's what happens when you have negative eigenvalues or negative poles. So the domain of attraction is all of R to the n. So from any initial condition, you will drive the closed loop state all the way to the origin. So the origin is attracting your state in some sense. But this is not really necessarily going to happen for your nonlinear systems. And so, for example, you can have, so just sort of thought experiment wise, pretend that this is like state space. I have 3 isolated equilibria. So for sure you can see this by saying, okay, I start here and I stay here. This is an equilibrium. So this equilibrium over here clearly is not globally attractive because any solution I start here doesn't go there. So, and also there can be unstable steady states. So it might be true that I start infinitesimally off this one and it just goes to this one, or infinitesimally on this side it goes to this one. And so it never goes to that one unless I start there. So that's also not attractive. But then these other ones might be attractive, but only from a range of points. Like this one might only attract solutions in this range, and this one might attract them from everywhere else, for example. Like, oh, I attracted all the other solutions. So then we do have to consider our domains of attraction. So that's really important in control and systems theory, because, so for the moment, consider no control. So in that case, it's essentially like you're applying the steady state input maybe off your steady state. So open loop. So then is it open loop stable or open loop unstable? And then it will be open loop, so no control. Like you'll be able with the steady state input so that your equation is no longer a function of the input, it's just a function of, it's just like has the steady state built in there. The closed loop state will only go to your actual steady state that you're trying to drive it to for a certain range of initial conditions in most cases. So if you start too far away, probably your control or like your steady state control action is not going to drive you all the way to the steady state. So it's really important to understand, because what it means is that's very different from what happens in control class, where you just say, oh, I applied the steady state input, it drove me to the steady state. Now we're like, okay, well, it might not. It depends where you start. And then it's also very important that then when we design controllers, we try to give them domains of attraction that are sufficiently large, so that we try to make it so that under the controller, so when you add control to something, you actually change its dynamics. So if I have x dot equals ax plus u, now say that the steady state input is u is equal to 0. So when I said u is equal to 0, x is equal to 0, everything is equal to 0. So there's my steady state input. So pretend it was like x squared plus u. So pretend, I don't know what this domain of attraction is. I think it's actually nothing. Now it's infinity. Now it's everywhere. No, I guess not if the inputs are certain things. So I don't know. Just pretend for a second. You can see that by adding this u, I've changed the dynamic. So if I was instead to make, so when u is 0, I just have this. Here's the whole dynamics. When u is not 0, I have x dot equals negative x squared. Say that u is equal to ax. X squared plus ax. Now, fundamentally, because I've chosen this control law instead of PID or whatever, the right-hand side is acting differently than it would be. So it's giving me a different time derivative than if I was to use the steady state input. So with this control law, I've actually literally changed the dynamics of my system. That's what control always does, and that's why control is awesome. And it can actually cause stability of unstable steady states, because now you have like a new steady state, right? So the steady state is no longer what it was before, or if it is, it could change stability. So negative x minus a. Okay, so now I actually have, now that I have this controller, I actually have a new steady state compared to the one that I had before. And so I actually changed the dynamics so significantly that I can do all kinds of stuff. I can eliminate steady states like this. So like if I have multiple steady states, and I might be able to find a controller that makes it so now I only have one steady state under that control law. So then I could try to make that globally stable. I could try to make a globally stable steady state using my control law and all those different things. So I can make unstable steady states become stable because I literally changed the dynamics. And if I have a different dynamic model, now I can make different steady states stable or unstable. So that's part of why this domain of attraction idea is so important, is because if we want to change the stability of a steady state, then we say like, okay, well now how far away from that steady state can I start before I am driven to it, if I just actually literally changed its stability or all the opposites. And so the last thing that, last thing just really quick is that if I have, there can be cases where, so for the linear systems, when we have the eigenvalues are negative or the poles are negative, we have like a bounded input, bounded state type of stability where you give it a bounded input, and what you get back is a state that remained bounded if your input was bounded. So that would also mean bounded disturbance. So taking a similar rule to the input. So x dot equals ax plus bu, or plus like bw, for example. So you give a bounded value here, bounded state if your eigenvalues are negative. Then
that's the definition that I was told, that is a stable system, but we cannot define this way.
No. So when we talk about, so that would be loose style writing.
Mm-hmm.
That doesn't account for kind of the fact that linear systems are actually part of the class of nonlinear systems. So we have to talk across the board, everyone the same, or else it's very confusing. Okay. So we never talk about systems, stable or unstable.
Okay.
Yeah.
Thank you.
Yeah, that's a good question though. But then, so for nonlinear systems, what can happen is I can give like a bounded input, something, or a bounded disturbance, bounded input, and I can get, so here W is going to 0 as T is going to infinity. But it can happen that for certain systems of equations, like which one? Apparently, I was told that this is one that suffers from this problem. That I was told that the solution to this is x of t is equal to root 2t plus 2. I've not tried to verify that, but I guess you could plug it into both sides and see. So then, in this case, what happens is that time is going, as time goes to infinity, x is going to infinity, even though the disturbance was bounded. So then just all kinds of weird stuff that you never think of can happen with nonlinear systems. So then that's why it's good to do the thing we're going to do next time, which is to start saying, like, well, I hope we do it next time. Maybe we will only do face portraits next time. Well, maybe we'll do both. But essentially to start saying, like, okay, what am I going to do about these things? I don't like some of this behavior, and I'd like to make sure that the systems I'm talking about don't have that, because I don't want to have to account for this in all my proofs, right? I don't want to have to make separate proofs to be like, and if this weird thing happens, now do this. And if this other weird one's happening, now do this too. And then so just like, okay, how can I just eliminate these? Too much trouble. And then, so that's what we're going to be doing pretty soon. And that's where some of the stuff like locally Lipschitz that you've probably seen in that paper, Dominic, that's where that actually starts coming in, is locally Lipschitz is one of the properties that you can add to things to make them behave much more nicely, so that you try to like eliminate some of this craziness and stuff. So anyway, that's advanced control number 1. Yeah!